So this is the second part of the organic review without practice questions. We'll get to the practice questions later. But here we're going to talk about some reactions and some important reactions that we need to know. So the next functional group, so to speak, that we're talking about are called esters. And these occur in reaction between carboxylic acids plus alcohols. Okay, so let's take a look. Carboxylic acid, so any example, I'll do propanoic acid. Plus, I will put the alcohol in a different color, OH, CH2, CH3 would give me ethanol. So eth and all, because there's two carbons plus an alcohol is ethanol. Here I have 1, 2, 3 carbons, so it's prop and oic acid. Right? So now what I'm going to do is basically what happens in a esterification reaction is this OH and this H combine to give me H2O water and kind of disappear. The water comes out, if you will. So this bond now continues to this oxygen. So if we were to draw the compound here, it would look like the acid part, CH2C double bond O, but I've lost this OH. I no longer have that OH. So now connecting that bond here is OCH2CH3. Right, this part, my alcohol part. Right, so it's very easy. You just write your acid and your alcohol right next to each other so that this OH, OH are kind of lining up. You remove an H2O, and then you connect whatever the pieces that were remaining, right, with the bond. And then we have some part that comes from our acid. We can recognize that basically because of the C double bond O here. So this is indicative of the acid, and wherever the O is, that part was your alcohol part. So when naming this, we have to be careful. We're going to start with the I mean, you should usually start with the alcohol, with the acid part, but we're gonna write that after. So the ending for an ester is the not just. So I mean, yeah, but so there's two things that it came from. So one, we know that it came from one part came from the alcohol, one part came from the acid. So we have to say, first we're going to do the acid. We're going to say prop and O8, because that signifies that it's an ester. And then from the alcohol, well, I should do this in colors. Propan OH, signifying that it's from the acid. And then from the alcohol, I have ethyl propanoate. So ethyl, the YL signifying that it came from the alcohol, and the O8 meaning that it came from the acid. All right, so this is the thing for an ester. Again, we have to know how to name these things and from which alcohol acid they came from. Similarly, there's there are a class of compounds called amides. The endings look like il and then amide, so it's very, very, very similar to an ester. Here we're going to mix a carboxylic acid, and we're going to add that to an amine, and that's going to give us an amide. So we'll do different examples. We'll do let's say we'll do HCOOH. So this is an interesting, this has only one carbon, but it has a carboxylic acid ending. So this is a methanoic acid. Let's get an amine. Let's do NH2. So I've just drawn the H out so that I can eventually take a CH2, 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 CH3. So this is, sorry, so that's butanamine. We know that because there's 4 carbons, so butan, and then NH2 means amine, right? So butanamine, and then we are going to, again, take a water out of that. So again, we're left with an acid part, HC double bond O. And then we add on to that, the bond continues over here, so NH is left on top, and then we have CH2, 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 CH3. Again, you could, I know I just put the 2, 2, 2, 3 from somewhere, but if you started off with like C, 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 and then you counted, okay, this carbon has 1 bond, so H3, 2 bonds, so H2, 2 bonds, so H2, 2 bonds, H2. That's where you get it, right? So it's not, I didn't pull that out of anywhere. I'm doing the same thing. Whenever you have to add hydrogens to carbons, you count how many bonds the carbon atom has, and then you add the hydrogens accordingly. Even if we go back to our previous thing when we did, when we did ketones, I didn't really add the hydrogens here, but look at this carbon. It has 1, 2, 3, 4 bonds already, so no hydrogens. This carbon has 1 bond, so 3 hydrogens. This carbon has 1 bond, so 3 hydrogens. You're always looking, seeing how many bonds, and then adding the hydrogens, right? So we'll go back to where we were. And so while naming this compound, you go, again, you start with the acid part, so that's methanamide, and then you have a butyl for the amine part. So it's butyl methanamide would be the name of this compound. The methanamide coming from the acid part and the butyl coming from the amine part. Very similar, if you'll see, to what we did with the esters. It's just instead of the OH, there's an NH2. Instead of an alcohol, there's an amine. Right? A couple more things we have to go over. You have to know the exact structures of 3 related compounds to a new kind of compound. It's basically, okay, I'm going to draw the long form once, but you don't have to draw that again. So it contains 6 carbons in a kind of ring. They're all like in a circle, but it's 6 carbons, so it's a hexagon ring, and then there's alternating double bonds. So we can start anywhere, but there's a double bond here, you skip one, double bond here, skip one, double bond here, skip one, and then you get back to the original double bond, right? So this is a structure, and again, you can count each carbon. This here has 1, 2, 3 bonds, so it has to have 1 hydrogen, 1, 2, 3, so hydrogen, 1, 2, 3, hydrogen, 1, 2, 3, hydrogen, 1, 2, 3, hydrogen, 1, 2, 3, hydrogen, right? So this has 6 carbons and 6 hydrogens. This structure is called benzene. And a shortened structure looks like this, where each carbon is just you can just draw a hexagon. Each carbon is just a kind of point. You don't even have to mention the hydrogens. It's automatically assumed that this carbon has 3 bonds, so you know there's 1 hydrogen there. You don't even have to write it because it's very common knowledge to assume that that's the hydrogens. Again, this can only be done with dots. If you're actually drawing out, if you're actually writing the C, you have to put the hydrogen there. So don't do add the hydrogens here. It's just for benzene, it's a special case. We're not going to do the hydrogens because we're drawing it in a special way. So this we have to know is benzene. One more thing we have to know is if you have a benzene and then a CH, and then another carbon that's coming off of the benzene, so that'll be CH3. This is called toluene. And then again, a benzene ring. This is just, I'm drawing it the other way just to show that I don't really care where I start drawing my double bonds. I just double bond, skip, double bond, skip, double bond. And if I have an OH group sticking out of there, I have what is called phenol. So phenol is the compound that's called. If I have a benzene ring and an OH group. There's obviously a large number of aromatic compounds, as they're called, most of which have to do with derivatives of benzene, so a bunch of stuff added on to the benzene. These are the main three that we're going to be talking about. These are usually the most important ones. Benzene, toluene, and phenol, those ones that show up the most in organic chemistry. So we will focus on those. And now we shall do a quick lesson on polarity and its effects. So we talked about before whether bonds were, we talked about it in class, we didn't really do a video series on it, but basically we can decide whether bonds are polar or not. So in order to do this, a rough sketch, very, very rough, very inaccurate, but serving our purposes, is, again, I have provided you a new periodic table. We don't really need it because I'll be giving you this kind of ladder. You have what are called electronegative compounds like oxygen, nitrogen, fluorine, chlorine, main ones, even bromine, iodine, right? These are all polar stuff, not polar stuff, but electronegative. And then we have a kind of ranking, and then we have carbon and hydrogen are relatively not electronegative. So electronegative basically means how mean you are when you're so when they form covalent bonds. We know that's electron sharing, and some compounds don't share equally. So carbon and hydrogen don't want too much of the electrons, but these guys, oxygen, nitrogen, they want a lot of the electrons. So they're going to steal or take more of the electrons. They're meaner, and therefore we have the distinction between polar and non-polar bonds. So if there's any mixing between these two groups, if you have a mean person with a not mean person, so this is the mean side, this is the not mean, or by mean I mean electronegative, and not electronegative relatively. If you have a mean with a not mean, that would be a polar. So mean plus not mean. If you have a mean mean or a not mean bond, that's a non-polar. So for example, polar bonds would be carbon oxygen, carbon fluorine, carbon bromine, because I'm mixing one carbon with one of these guys. Hydrogen iodine, hydrogen fluorine, hydrogen oxygen. All of these are polar bonds because I'm mixing one of these guys with one of those guys, right? The ones on top. A non-polar bond would be carbon hydrogen, because that's a not mean pair. Oxygen chlorine, or fluorine oxygen. Again, this is not technically true. This is probably a polar bond, but again, that's getting into the details of it. In organic chemistry, we're never going to see oxygen chlorine bonds per se, so we're not going to worry about that. But just know that the important thing is to recognize the difference between carbon hydrogen is non-polar and carbon bonded with any of these guys is polar. That's the bottom line here. And so as long as you know that, you should be good. So again, carbon hydrogen is non-polar. Nitrogen oxygen is non-polar. Fluorine chlorine probably non-polar. Non-polar. Oh, sorry. Carbon oxygen here. This is apolar. Right? Carbon nitrogen is polar. Polar. Again, I'm just looking. Carbon to anything other than a hydrogen is polar. Hydrogen to anything other than carbon is polar. That's bottom line. It's not as straightforward as that, but we can kind of, let's say, estimate, if you will, for lack of a better word. So, we're going to be talking about two effects of polarity. One effect is the solubility. One effect is the melting point. So what we have to understand about solubility is that like dissolves like. So polar solvents dissolve polar substances. Non-polar solvents dissolve non-polar substances. So water. So for our purposes, we're going to be looking at two solvents: water being a polar solvent, and hexane being a non-polar solvent. So anything that is polar dissolves in polar. as in water. Anything that is nonpolar dissolves in hexane. So because hexane is nonpolar. So we'll do some examples. CH4 is nonpolar. It has only carbon-hydrogen bonds, right? So it's a nonpolar molecule, so it will dissolve in hexane. C2H5OH. This has carbon connected to hydrogens, so that's kind of nonpolar, but it also has carbon connected to an oxygen, oxygen connected to hydrogen. These guys are polar, so because there's a small bit of it is nonpolar, a large bit of it is polar, this will most likely be dissolving in water, because there's more polar than nonpolar parts. It's not a really exact science, but that's the way we're going to think about it, right? Because there's a small nonpolar bit and a large polar bit. There's more polar stuff. So it's going to dissolve in polar, as in water. This is C10, 4, 5, 6, 7, 8, 9, 10, OH. So this part here is polar because it has a carbon-oxygen bond and an oxygen-hydrogen bond, but all this part here is nonpolar. This nonpolar part is very much bigger than the polar part, so it kind of defeats or trumps the polar part. So the compound as a whole will dissolve in hexanes, a nonpolar solvent, because the nonpolar part is bigger. I2, we saw that any two compounds at the top is nonpolar, and therefore this will dissolve in hexanes. CH3NH2, again, you have some nonpolar bonds, but again, you have a lot of polar bonds. You have two NH bonds, a CN bond. All of these are polar, polar, polar. So basically, all of the entire molecule is polar because it has polar bonds here, here, and here. There's some non-polar bonds, but it's not really like, oh, you can count the number of non-polar. It's just you look at the thing as a whole. You draw a circle around roughly where the polar stuff is, and that's the polar. So the polar stuff is all around here, basically. Which includes those bonds, right? So this is a polar, and so it will dissolve in water. All right, so we'll do more practice with the practice questions. We're going to jump along for boiling points, which we have to remember to write down the following trend. So we did a kind of special cases here. I didn't say why they were special, but they're special not because of their solubility. Solubility does not matter if there's an HO or NH. That doesn't affect the solubility really. The important thing that affects is the boiling point. So special H bond molecules are molecules that have an HO, an HF, or an HN bond. So let's look at the first case. You have a CH4, you have a CH3, CH2, which is abbreviated as C2H5. OH, so you see the special OH bond here. Then you have propanone, which is CH3C double bond OCH3. Right, so these are the three I'm asked to compare. Non-polar molecules will be the least boiling point or lowest boiling point. Then comes polar ones, like this is a polar molecule because it has a C double bond O bond. But it doesn't have any of these special H molecules, right? Even though there's a hydrogen and oxygen, they're not connected to each other. So that will be next on the line. And then finally will be the special H bond molecule because there's an HO bond, CH3, CH2, OH. So that is the order of boiling points. Similarly, we can compare this. This is non-polar, so it'll be last. HCl is not a special H bond, but it is a polar molecule, so that will be second. HF is a special H1 that's included, so that will be last. So it's again just identifying which ones are which and putting them in order. That's basically what boiling point is. Again, boiling point is the temperature at which a liquid becomes a gas. So things like benzene is nonpolar, methane gas is nonpolar, carbon dioxide is nonpolar, that's a gas. All of those are gases at room temperature, but things like water, because water is HOH, this has two of these special H bonds, that's a liquid at room temperature. It has a much higher boiling point of 100 degrees Celsius. And just to give you some context there as to what exactly we're talking about. So the next video will be on the practice and the review questions. So I'll see all you folks in class.